In this video, we'll give an introduction to matrices. So the next step up from vectors gives us matrices. What are these? Well, these are, instead of being a column of numbers, these are now an m by n matrix isn't a rectangular array of m times n numbers. So this matrix will have m rows and n columns. And so something like this would be a 3 by 4 matrix because it has 3 rows and 4 columns. If we call a matrix capital A, we usually use capital A's for matrices. We use notation A sub ij to denote the number in the ith row and jth column of the matrix A. So this basically allows us to pick out individual elements from this matrix as we go forward. So for instance, for the matrix I have right there, the element A23 is going to be in the second row, third column of A, which will be -1. A14 is equal to 9, and so on. So I can pick out individual guys using these subscripts to denote the row and column in that order for this matrix. As a quick explanation of this, we can also note that the way we define vectors, a vector with n components is just an n by 1 matrix because it has one column, it has everything all in one column, so there's n rows, and these vectors we discussed before are all just n by 1 matrices. So what can we do with matrices? Well, just like vectors, we can add if they're the same size, and we can multiply them by scalars. All that stuff works the exact same way as it does with vectors. So I have a matrix 1, 2, 3, 4. I want to add to a matrix 1, -1, 2, -3. I can just do that. I just add across. Each component gets the sum of the components that it had before it. So 1 plus 1 is 2, 2 minus 1 is 1, 3 plus 2 is 5, 4 minus 3 is 1, and that would be the sum of those two matrices. I can also multiply by scalars. 3 times the matrix 1, 2, 0, 1 is going to be 3, 6, 0, 3. Just multiplying that scalar to every component of the matrix. Every number in the matrix is multiplied by the same scalar that's out front. Again, if they are not the same size, addition is not defined. That's the same as it was for vectors. What about multiplying matrices? Well, it turns out that we can actually define a way to multiply matrices that makes sense. This actually comes from the idea of linear transformations of vectors as matrices, but it falls back to our dot product. The idea being that the ij entry of the product, AB, is a dot product of row I of A and column J of B. What does that look like? Well, if I have two matrices that I want to multiply, let's say I want to look at the first entry 1, 1 in the product. That means I'm going to take row 1 of the first matrix and column 1 of the second matrix and take the dot product of those two vectors. Right? If I extract that first row of A, that's a vector. If I take the first column B, that's also a vector. I'm going to dot product them together to give me the first entry there. If I want to look at 1, 2 of here, I'm going to take still the first row of A, because I'm still in the first row of my answer, and now the second column of B, and dot product those together to get the 1, 2 entry of the product AB. And you do this for the entire matrix in the product that you want to get. And by doing this, we can see when this will be defined. Right? It's only defined if the two vectors I want to take the dot product of are actually the same length. So if matrix A is m by n, if matrix B is p by r in terms of dimensions, then this only works if n equals p. The number of columns of A, which is the number of elements in each of these vectors, equals the number of rows of B, or the number of elements in each of those vectors. So we need n equals p for this to work. And if we have that, our product here will be of dimensions m by r, basically these outer two terms here. So these two have to match, and then the dimension, the output is the outer dimensions of this sort of setup here. Because for every choice of row or column here, that is the choice of a row here, so number of rows equals number of rows here, or column here, so number of columns here is number of columns here. Just as an example of that, if I take the matrix 1, 2, 3, 4 again, I want to multiply it by something. Now this matrix here must have 2 rows because I need the number of columns of A to equal the number of rows of B. So this must have 2 rows as we defined. So let's make this a 2 by 3 matrix just to see what happens. And we can now find this product. Based on dimension-wise, this is a 2 by 2, this is a 2 by 3, so my answer should be a 2 by 3 matrix. Now, in the first spot, I'm going to multiply the first row of A, the first matrix, dotted with the first column of the second one. So I'm going to get 1 times 0 plus 2 times 3. For the next entry going across, it's the same first row, 1 times 2, dotted with 1 times minus 1. So I will get 1 times 1 plus 2 times minus 1. We can keep going to fill out the entire matrix. Then we just compute all of these different sums to get our matrix product. And as expected, that is a 2 by 3 matrix. So that's the idea of matrices as sort of an extension of vectors, how operation matrices are defined, including matrix multiplication, and the idea of sort of where this all comes from to give you a foundation for what we can do with matrices going forward to do more complicated, more involved things with these objects going forward in linear algebra.